Hello, M2 crew, me, Dr. Gray. I wanted to work through with y'all one of the questions from one of the multi-part questions from your homework, your equilibrium homework. Okay, so this is the very last question. And it starts out with a sample of nitrosyl bromide, NOBr, been decomposed according to the reaction or according to the equation. That goes to 2NO plus Br2. Okay, now our coefficient out in front of the NO, there we go. So this is all balanced right here. Now the first question asks us to, well, solve for our equilibrium constant, or our K sub C. And the way that I like to approach this is, well, we're going to have concentrations of our products, NO, that's going to be squared because that we've got that 2 coefficient that has to be an exponent here. And then we've got Br2. Okay, these are our products, products over our reactant. We only have one reactant, and so we've got NOBr, that's going to be squared. Okay, now that's kind of the easy part of this. This question is a little bit more involved, though, because there are a couple of steps before we can actually go about solving it. This setup right here, we're done. But what do these brackets mean? These brackets mean we have to calculate a concentration. So that means we need to know the number of moles and we need to know a volume. Or if the question just gave us concentrations, we'd be in great shape. But that's not the case. Instead, this question gives us masses. So it gives us masses and a volume. It says that this is all taking place in a 5-liter reaction vessel. We have 3.22 grams of NOBr. And this is all at equilibrium, 3.22 grams of NOBr. We've got 3.09 grams of NO. And finally, we've got 8.23 grams of Br2. Okay, so these masses alone aren't really going to give us what we need. Instead, what we need to do is we need to take these masses and get moles. And then once we get those numbers of moles, then we can take the number of moles and divide it by 5, because that will give us a concentration. Now, this 3.22 grams is going to be approximately 0.029297 moles of NOBr. Okay, we divide that by 5 to give us a concentration, and that will give us, I'm going to go ahead and write this in a little bit of a longer display here, this is my concentration of NOBr at equilibrium, 5.8594 times 10 to the negative third. That's going to be squared. Okay, now my next number is going to be the mass of my, let's go with the mass of my NO. That would be 3.09. Well, that 3.09, that is 0.0.0299 or 10298 moles. This is also divided by 5 to get a concentration. So I'll plug that into my calculator. 0.10298 divided by 5 gives me 0.020596 times, yeah, it's not times 10 to anything. Boom, boom, there we go. And that's going to be squared. Now Br2, I've got 8.23 grams, so I need to type in that 8.23. 8.23 grams of that is equal to 0.051499. That's going to be it. So I'd plug all that in, and that's going to give me my K sub C. So my equilibrium constant, because I converted, oh, wait, almost made a mistake. That was my number of moles. Here we go. So this was 0.051499. This I'm going to divide by 5. Okay, 0.051499 divided by 5 gives me 0.0102998. That's my molarity. Okay, so now I've got all my concentrations. So I'll take 0.020596 squared times 0.010998. I'll plug that in. 0.020596 squared gives me that number times 0.01029998 equals, now my numerator, I've got 4.369 times 10 to the negative 6 divided by 5.8594 squared, 5.8594 to the negative 3rd, square that, I get 3.433 times 10 to the negative 5th. Okay, so now I'll plug all that in. I just had to pause because I wanted to make sure that I plugged all my numbers in right. 4.369 times 10 to the negative 6th divided by 3.433 times 10 to the negative 5th. That gives us 0.127264783. Obviously, mastering chemistry is asking for a slightly different answer. It's asking you to basically round that question down or round that answer down. But that's effectively our case of D. There we go. Now pause. All right, so the next part of this problem, well, it goes on to say, what is the total pressure exerted by this mixture of gases? Now, this is changing gears a little bit, but it's something that's within your, I guess, kind of your area of expertise, because you know that the ideal gas law is PV. So I'm just going to go ahead and draw a little line, dividing line to separate our problems. I'm going to go over here, start in the lower left-hand corner. And you know what else? I'm going to switch to green pen. We know that for part 2, you know what? I'm going to use a whole new page. For part 2 of this problem, this is asking, well, total pressure. We know that the ideal gas equation says PV equals nRT. Now, if it's asking about the total pressure, what we need to do is basically rearrange this equation to be P equals nRT over our volume. Okay, easy enough. Now, volume, do we have that? Yeah, it's 5 liters. Does the problem say anything about temperature? In the words of my relatives from the Midwest, you betcha. Temperature is 100 degrees Celsius or 373 K. Now, our R value is 0.08206 or 0.0821. This difference right here is probably pretty negligible in terms of doing your overall calculation. I'm going to go ahead and erase the 0.08 or 0.0821 just for the sake of, just for fun, really. The last value that we need is N. What's N? N is the total number of moles. Do we have the total number of moles? Well, not off the cuff, but if we jump ahead or jump back for just 1 second, did we calculate our total number of moles? We did. We took each one of our masses, NOBR, and converted to figure out the number of moles of NOBr that were present at equilibrium. Did we determine the number of moles of NO at equilibrium? We did. It's right here. And finally, we did the same thing for Br2. Okay, so that's our total number of moles that were present at equilibrium. So 0.029297, 0.10298, 0.051449 or 499. That's our total number of moles. If you combine those, you can plug that in here. Why? Because this is simply correlating the number of moles to our total pressure. So part 2, you have this, you have this, you have this. Sorry, that's a 5L for liters. The last thing that you need to do is combine and add up those total number of moles. Plug it all in, and there's your pressure. Now, some of y'all might be saying, because the question does prompt you for, well, what are the units for pressure? Well, I'll give you a little bit of a hint. Your units for your ideal gas constant are going to be moles times Kelvin liters atmospheres. So when you plug all those values in against these units right here, you're going to be left with only one unit. Okay, so I hope that makes sense. And I hope that you can deduce which your units are. Okay, so now part 3. I've got enough space here that I can work with this. Part 3 reads, sorry, I'm toggling between windows and everything like that. Part 3 says, what was the mass of the original sample of NOBr? Express your answer to 4 significant figures and include the appropriate units. Okay. How do we figure out the mass? It's a little bit tricky. We're told about what's present at equilibrium. And you might be thinking, I've probably got to do an ice table. But before you do that, let's think about this one. In a chemical reaction, you have masses of your starting products, then you have or starting reactants, and then you have masses of your products when the reaction's either done or it's reached equilibrium. Does the total mass ever change? Sure, one reactant, the mass of that will go down. And what happens? Well, the mass of one of the products goes up. We have what's known as a conservation of mass. That has taken place. So the total amount of mass, or the total mass, has been conserved from your starting point to your concluding point. All right, everyone. I hope that was helpful, and I hope you have a great day.